So after this this first introduction on physically based virtual twins, I propose a discussion, in fact, on different prospects or improvement or new applications or other applications of such virtual twins. For instance, here, in the previous virtual twin dedicated to the simulation in real time of the welding process, we have considered all the balance equations of the physics. I mean, balance of mass, linear and angular momentum, first principle of thermodynamics, second principle of thermodynamics, and given stress, nonlinear stress strain law with possible internal variables. Some other possibilities can be used today to build other kinds of virtual twins based on experimental data, which they are called, for instance, data-driven virtual twins. So it is included in the general framework of data-driven computational mechanics, which is very active at that time. For instance, the ideas of Ortiz and many authors in this area. So the idea is to, globally speaking, keep in mind the fundamentals of the physically based hybrid twins, virtual twins, sorry. However, we don't want to explicitly write a specific nonlinear stress strain law. Okay, we want to ensure the Newton law, linear and angular momentum. We can possibly have in mind to check or to ensure first and second principles of thermodynamics. However, we don't want to explicitly write a given stress strain law, and we replace such a relation by experimental data. So, for instance, here, such an approach is based on a subspace in blue, which concerned the physically based part of the virtual twin, and also in gray, the different nodes, which are a couple of nodes. I mean, for instance, stress, strain, quantities from experimental data. Okay, so instead of trying to identify a stress strain law based on a specific theory, we replace such an information by the material data, and then we develop iterative processes based on specific Lagrangians in order to reach at convergence a good compromise between a set of partial derivative equations which are physically based and the material data. Here is the first example. It is another way to show the same idea here. It is on the right a general data-driven framework, which is a compromise between a set of a set of partial derivative equations physically based, which corresponds to the blue line, and the black points corresponds to the data experiments. And so instead of trying to identify a constitutive law physically based in red, we only focus on the black points in order to build a compromise between the governing equation and the experimental data, which is at the end the data-driven solution, and it can be compared to the classical solution in a finite element framework, for instance, based on constitutive law, standard constitutive law. So in order to develop the data-driven solutions, we can use such a Lagrangian, for instance, where the star quantities on epsilon and sigma correspond to possible experimental data. There is a key point, in fact, in data-driven modeling in order to build, for instance, virtual twins for welding or the kinds of multiphysics or multiscale problems. We assume that we have data. We assume that we have experimental data. Or in fact, in practice, it is not so easy in solid mechanics, for instance, to have experimental data. Here, for instance, you can imagine to have digital image correlation in order to have experimental data on a surface, or microtomography in order to have experimental data, displacement field and stray field in the bulk of a component. However, it is not so easy to have the dual quantity, I mean the stress field, in terms of experimental data. So yeah, we have also to account for the ability of the specific physics, I mean, for instance, nonlinear solid mechanics, to be able to have such data. Okay, so particularly the stress field. And then we can develop also in a specific multiparametric space with techniques linked to deep learning and artificial intelligence. We can also develop specific virtual twins. This is the first attempt to develop data-driven virtual twins. So maybe it is we can make the difference between a virtual twin and a digital twin, and maybe it will be the topic of Paco Chinet's this afternoon on a very interesting concept of hybrid twin, a compromise between a completely physically based virtual twin and a virtual twin which comes from more experimental data with no physical content. Okay. And such approaches are already of interest even with elastic plastic models, as you can see here. If you compare a finite element solution and a solution from data-driven, even in the case of non-smooth laws with multivoc laws, I mean, you have different possibilities of paths in order to reach a same set of stress and strain in elastic plastic models. And even in this case, data-driven models can follow a path, an history path in the solution at a given point of the model. Now, I want to switch on another topic, which concerns also virtual twins. I have focused on the previous presentation on material parameters. If I consider the space parameter, the time parameter, we can add material parameters. This is what we have done on virtual twins dedicated to welding process, for instance. We have also focused on, in a very simple case, on each source parameter, okay, so an external load parameter for the system. And a very interesting topic also concerns geometric parameters. We have already discussed on the thickness, for instance, on the welding process of a plate in order to develop virtual twins with a very simple case of first attempt of geometric parameters. But in the general case, it is a very, very complex task where we have to compare, for instance, completely different geometries. And a very interesting example comes from biomechanics, where you can, for instance, have to compare different kinds of meshes, which comes from specific, here, for instance, it comes from possibility applications of virtual twins to aortic aneurysm, okay? And in this case, if you compare two different kinds of bodies, in fact, you have completely different geometries. So is it possible to build virtual twins on the geometric point of view in order to build in real time a virtual twin where the parameters are the shape of the mesh, okay? And you want to modify the geometric parameters in real time in order to have on the new mesh, okay, in real time different fields. different fields. I mean, I don't know, in FSI, fluid structure interaction, you can be interested in the displacement field, the pressure field, the velocity field, and so on, and the stress field, and strain field. And is it possible to put on a new geometry in real time the good fields according to balance equations, okay, to the good physics? So it is quite challenging because in practice, when you proceed to 3D imaging, you have completely different meshes. In practice, it can be a triangulation of the surface. And from this information, there is no simple way, in fact, to compare different meshes in order to develop a virtual twin of the geometrical parameters. Because we have a constraint. The constraint is the fact that the two meshes have to live in a same space of finite dimension. I mean, for instance, we don't have exactly the same number of triangles, the same number of nodes, for instance. So how to compare such meshes in a finite way, in a finite dimension space? Okay. So what we propose, this is my next talk, to focus on such parameters, I mean geometric parameters, a general way to compare different meshes in order to build specific virtual twins. So here, the idea is the following. Okay, does it work? Yes, it works. Here you can see, for instance, a very interesting technique, which is a morphing technique. I don't know if it works on the right. Okay, I can try again. Yes, it works one time. Morphing technique, if you have the same number of nodes and the same quads, here it consists in quads, meshing of quads on the boundary of the geometry. If you have the same number of nodes and the same quads on the same part in the topology point of view of the mesh, then you can develop morphing techniques in order to switch from a geometry to another one. And then the question is how to be able to build from a triangulation of two meshes a new quad meshing of the boundary, which is compatible between the two initial meshes. So the discussion involves, in fact, topology considerations and also the ability to build a quad meshing of a boundary, and we will see later a cuboid decomposition also of the bulk of the mesh if you want to use a virtual twin where you have bulk information, I mean 3D fields, not only on the boundary, but also in the bulk. You have to proceed on a quad decomposition of the boundary and also a cuboid decomposition of the bulk. Okay, so for instance, in this case, a very interesting cuboid decomposition, as we will see later, is based on a very important result of topology, which is quite new, less than 20 years. It is based on what we will call Part decomposition. The Part decomposition, for instance, here consists in building, in fact, something like a sphere with 3 holes. A Part is no more than a sphere with 3 holes in a topologic point of view. And here, in blue, red, yellow, and green, you can see a Part decomposition of the two topologies with different meshes, but in fact, it is the same topology globally. And then we can build a reference cuboid decomposition very efficiently. And from this reference model of quite complex meshes at the beginning, and from this reference model with a Part decomposition, we can build, we will see later, a quad decomposition, a quad meshing of the boundary, and a cuboid decomposition of the bulk. And then we can automatically build a quad meshing which make a strong link between different meshes, not only in the boundary, but also in the bulk with the cuboid decomposition. And then it is of interest because when you have a quad decomposition and a cuboid decomposition, you have a tensor product. You have a tensor product decomposition of a quad and also a cuboid, okay? And then in this case, you can imagine to use the previous concepts, because if you have a tensor decomposition of the parameterization, not only on the boundary, but also in the bulk, then you can use a parametric space as a sum of product of 1D functions because you have a tensor decomposition on the geometric modeling of such meshes. So this is a general idea, and this strategy is well suited for separated variable decomposition of the geometric parameters. This is the aim. This is what we want to do in order to use the previous techniques, sparse grids and so on, and separated variable representation. I mean high-order proper generalized decomposition for the geometric parameters. Okay, so this is why we want to focus on quads and cuboids. In other words, a parameterization of the boundary and also the bulk. So we have to develop important concepts in topology in order to reach this goal. I propose here an isogeometric analysis, a suitable Trivariate model generation dedicated to ROM with geometric parameters. It is a complex way to explain what I said before, but it is the same thing, okay? So the fundamental question is that imagine you have two meshes and how to compare the two meshes, okay? Because we have not the same number of nodes, the same number of triangles. For instance, if you have a triangle decomposition mesh story of the boundary. And in this case, it is a general, the aim is to be able to develop such an hybrid twin, a virtual twin. You have biomechanics application, but also here, this very simple example comes from linear elasticity, okay, solid mechanics. So the idea is to develop enough line stage, exactly the same strategy as before, where you have here geometric parameters linked to this problem. And here you can have geometric parameters, material parameters, and what you want is that in real time, the new geometry and the new fields on the new geometry in real time. Okay. So here, for instance, the quantity of interest plotted on this new mesh is the displacement magnitude in a linear elastic problem with specific external loads. Okay. So what is interesting here is that you can see in real time to modify specific thickness, diameter, or length, and you have in real time the new solution on the new geometry. Okay, so it is, we propose a general strategy based on isogeometric analysis, because isogeometric analysis is a very interesting way proposed by Professor Hughes in the United States. I think that more than close to 15 years ago, in order to make a strong link between CAD and meshing and finite elements. Okay, so this is an interesting first starting point in order to reach the goal of virtual twins on geometric parameters. So imagine that you want to make a link between computer-aided design and computer-aided engineering analysis, for instance, based on finite elements. You need a discretization, okay? And the standard way is to use finite element mesh, okay? However, as you know very well, finite element mesh, the description of the boundary strongly depends on the shape functions. And if you have here a curvature on the boundary, you have only an approximation of the curvature in the finite element mesh according to the degree of the shape functions. Okay, so from the exact geometry, what we call the exact geometry is the modeling in the computer-aided design software of the geometry based on, for instance, splines and nerves, okay? And the question is possible to put this information in the finite element model instead of having an approximation of the geometry. So if you want to modify a parameter, you have to come back to the CAD and then build a new mesh and so on. So it is quite expensive, not efficient, not frugal, okay? Instead of doing this, we can proceed in this way. Imagine that you keep information of the true geometry, and then you put it in the finite element model as an information of the interpolation on the boundary and the bulk. So it is what we call isogeometric analysis. In this case, the shape functions, in fact, are based on the functions that are used in the computer design, okay, splines and knobs. So it is a specific method. It is a generalization of finite elements, but assuming that we have this toolbox, then is a discretized model, the mechanical model based on finite elements or isogeometric analysis, we have the exact geometry. And such a model has a nice property to be based on quads and cuboids, okay? In other words, locally, you have a parameterization of the boundary and the bulk. In other words, you have a tensor decomposition. It is not possible to have a parameterization of a mesh based on triangles or tetrahedron and so on. What I want to say here is that when you have quad decomposition of the boundary in 3D and cuboid decomposition in the bulk, then you have, naturally speaking, a parameterization of the boundary and the bulk. Okay, so what is interesting also is that if you want to modify a parameter, you don't need to have to modify the computer design model. You can immediately modify the new discretized model because we have stored, in fact, the information of the true geometry. So the question is it possible to build, in general, a quad decomposition of a geometry, a complex geometry, and also a cuboid decomposition? It is an old dream, in fact, in meshing. Is it possible to build a mesh for complex geometries based on cuboids? So it is a complex problem in practice until recently. So what is important to notice also is the information that we have from computer design. In practice, we have not bulk information. We have only information of the boundary. This is called the BREP modeling. BREP modeling, which is used for CAD, is the basis for isogeometric analysis. However, as you can see here, we have only the information of the boundary. Okay, BREP from CAD doesn't contain information in the bulk. I mean, spline and knobs in the bulk. It is only defined on the boundary. So there is also the question in isogeometric analysis of the building of knobs and spline shape functions in the bulk of the mesh, which is not in the BREP model. Okay, so at the end, what we want to have is something like that. Imagine that you have a given problem with specific geometric parameters. Here, the position of the center of the circle and the diameter of the circle in this plate with a hole with given boundary conditions and prescribed loads. Okay. What we want to have is something like that, a virtual twin. And we want to have in real time the solution of such a linear problem with a modification of a specific set of geometric parameters. Okay, P1 and P2. So we have specific snapshots in the possible values defined for P1 and P2. Okay, and what we want at the end is in real time the solution in terms of fields, displacement, stress, and strain fields on such a problem according to the values of the two parameters, for instance. Okay, so here we can use a preview strategy according to the fact that we have the possibility to have a sum of product of 1D functions for each parameter. Okay, some information. Generally speaking, a key point in the proposed approach is the point decomposition. So I propose to give you some information from topology in order to understand the interest of point decomposition in such an approach. And a key point is the Euler characteristic, okay, which is 2 minus 2 times the genus of the surface minus B, which concerns the boundaries. And this quantity is of great interest in order, it is a very nice result from Etcher, as you can see in 2000, so 20 years ago, very important result. The number of points for a given surface, a standard surface with good properties of a smooth, good properties of regularity, I mean, okay? So if you have a closed, sufficiently smooth surface, then you can, with possible holes in terms of topology, you can define the number of patches that are required in order to cut this surface with different points. Okay? And the number of points is no more than 2 times the genius of the volume, the surface, plus b minus 2. So you can, it is a very, I'm very impressed by this result because here you have the number of points that are required in order to cut a surface, a complex surface in a sphere with 3 holes. A sphere with 3 holes is no more a point, in fact. And it is very interesting because 2 fundamental results. The first one is that a point decomposition, a point, in fact, is the unit of topology. Whatever is a volume, okay, it can be very complex with possible holes and so on. You have this result that you can cut this volume in different points, okay? So it is the first step. And you have the formula in order to calculate the number of points. The difficulty now is to be able to build these points. First difficulty. And the second result, very interesting result, is that a point, a sphere with 3 holes, can be decomposed in 4 cuboids. Okay? A point is no more than 4 cuboids. So what it means is that whatever is a closed geometry, sufficiently smooth with good properties of regularity, okay? Then you have a point decomposition, so you have a cuboid decomposition, so you can mesh it with cuboids. And it is a very important result. As far as I know, before this good property, it was not, we were never sure that it was possible to build a cuboid decomposition of a volume. And this is what we learned by this formula. Okay, so some examples. Imagine that you have a CAD of a given model. Here you have 3 holes, so a specific topology for this volume and this surface based on triangle, the meshing of the boundary. And here is an example. I don't give you the details for the algorithms, but here at the end, what you can see on the last step is a point decomposition. Okay, the blue part here on the right is a point. Okay, where the 3 holes are the 2 red parts and the blue part on the boundary of the blue surface. Okay, so it is a point. Here you have another point. So here you have 4 points in order to describe such a topology. Okay, so the difficulty is to be able to build the point decomposition, and then from this point decomposition to build the quad meshing of the boundary, and then at the end the cuboid decomposition on each point, and also the compatibility of the cuboid decomposition on the interfaces between the different points. Okay. Okay, so the idea is the following. First of all, a point decomposition of a surface based on triangles, for instance, triangle meshing of the boundary. Because if we are able to build a point decomposition, then we are able to build a cuboid decomposition of the bulk, and ensuring compatibility of the cuboid decomposition on the interfaces between the points, then we have a global cuboid mesh. Okay, so this is what I want to explain now. In fact, we can generalize the concept of points, but it is no more than an extension of points in some cases where it is better to proceed to other decomposition, which are quite simple in order to have whatever is the process, a cuboid decomposition. Okay, even we have a general result of points, sometimes it is better to locally improve a point in such a case in order to obtain a cuboid decomposition. But what I want to explain is that in theory, a point decomposition is enough in order to obtain a cuboid decomposition. or you can slightly improve the idea on specific geometries locally. Whatever you, the way you follow, you have at the end to obtain a cuboid decomposition. A last important result from topology concerns the boundary. Okay, for the cuboid decomposition, I will explain later how to proceed. However, we need another step. The question is the parameterization of the boundary and the parameterization of the volume. In fact, it is not so clear to have a quad decomposition of the boundary. Okay, because if we have a parameterization of the geometry, we have a quad decomposition of the boundary. Or if we have a quad decomposition of the boundary, we have a parameterization because the quad has two parameters, because the quad is intrinsically a tensor product locally of the boundary, which is not the case with the triangle. Okay, you have a non-uniform mesh or non-plane surface. You cannot, in a simple way, build a parameterization in terms of non-Euclidean manifold. Okay, a non-Euclidean manifold. A local parameterization of the boundary is not easy with triangle, but with a quad decomposition, it is very easy. Okay, so for that, there is a very nice method which comes from specialists of imaging and modeling of volume and surfaces, which is called Crossfield. So a Crossfield is no more than a way to build automatically a parameterization of a surface, for instance, based on triangles. So there are some difficulties in order to build the parameterization of an n-planar surface because you can have singularities and so on. For instance, as you know very well, it is not possible to build a parameterization, for instance, of a sphere with no singularities. Okay, you have a singularity on a sphere, and you can see it here. It is well-known theorem. So you have accounted for also the problem of the singularities in parameterization of a surface. Okay, so it can be done by the Crossfields. You have a strong link between the Euler characteristic of the surface, which is a closed geometry of a volume, and you have a strong link between the possible singularities and which are to be accounted in the parameterization of the surface. Okay. So here, as you can see, there is a link between the number of singularities and the Euler characteristic. Okay, some examples of the application of Crossfields. Imagine that you have a given mesh based on triangle, decomposition of the mesh, of the boundary, sorry. So we can proceed to a point decomposition. It is quite easy, in fact, to obtain a point decomposition. But the difficulty is to combine the point decomposition with the parameterization of the surface. Okay, so here the Crossfield reach this goal. It is a local field, okay? And this Crossfield, okay, so it is no more than a tensor product of two 1D functions, combination of two 1D functions, can be built automatically and with specific constraints in the fact that the parameterization of the surface has to be compatible with the boundary of the point decomposition. Okay, so it is no more than the fact that the parameterization has to be parallel locally to the boundary. Okay, so there is an iterative process that we can apply on the Crossfield in order to be compatible with the boundary. And at the end, we have a local parameterization of the surface, a non-planar surface put on the cuboid decomposition. How it works, the Crossfield, it is no more than a minimization process of this local field. It is very close to optimization of a standard minimization of this functional, minimization of an energy, in fact. It is a minimization of a specific energy, okay? which depends on the local curvature in a discrete point of view. It is a discrete differential geometry, and it allows to build at the end of this minimization process a local crossfield, which is the basis for this parameterization of the surface. As you can see, it is not so old, 12 years ago. Okay, so at the beginning, you have given non-optimized crossfield, and at the end, you have the good crossfield from the minimization of this very nice Fock energy, which is quite simple to develop. Okay, and then at the end, what you have, it is not only a cuboid, a band decomposition. We have not yet cuboid. So here we have a band decomposition and combined with crossfield, a parameterization of the surface. So here it is an initial crossfield, and after as you can see here, the parameterization of the surface here is not yet optimal because it has to be compatible on the boundary of the cuboid, the band decomposition, sorry. So now it is compatible, okay? So we have also to ensure the compatibility of the local parameterization of the boundary, okay? And then we have something which is quite interesting, a cuboid band decomposition and a parameterization of the surface, compatible with the boundaries. Okay, here at the end, what we have is a quad meshing. Okay, quad meshing based on band decomposition, and the starting point was only a triangulation of the surface. So starting from a triangulation of the surface, and based on the good properties of regularities of the surface and topology characteristics, I mean Euler characteristics, we are able to build automatically a quad meshing of the boundary on band decomposition. So we have to keep in mind that we want cuboid decomposition at the end. So here we have a parameterization of the surface, and we account for possible singularities and so on. So it is done in a very simple case, but it works also in more complex cases. If I come back to biomechanic applications here, we can use the same strategy, and as you can see here, we obtain from a triangle mesh of the boundary at the end a quad meshing of the same geometry. So it is quite interesting here because in this case we have the band decomposition, and at the end we have a parameterization of the boundary, so we are able to build a quad meshing of the boundary. And whatever is the geometry, if you have the same topology, you can build a reference geometry based on the same quad decomposition. So it is a way to make a link between different kinds of meshes, and the only link that you have between the different meshes is only topology. Okay, here it comes from an engineering application, and here biomechanic application. And now, the question is, from this parameterization of the surface, in other words, a quad decomposition and a band decomposition, okay, of the surface, we want cuboid decomposition of the volume. Okay, so now we have also to give you some information on topology in the 3D case of volumes. It is not so easy. In fact, it is an extension of the Euler characteristic, because if you remember topology, fundamentals of topology, Euler characteristic deals with only the surface of a volume. Okay, so if we want to consider the topology of the volume and not the boundary of the volume, we have to consider what we call the generalized Euler characteristic and the Betti numbers. Okay, so the Betti numbers are the physical content, I mean the geometrical content in 3D, the number of 3D holes, the number of cavities, and the number of holes, and so on. More interesting geometrical content of the generalized Euler characteristic is in a discretized point of view, what we call simplicial complex. I mean the number of vertices, the number of edges and faces, and possible volumes of the mesh. So it is what we want to use here. So there is a strong link between the generalized Euler characteristic and these numbers. Here is the formula, okay, why not? And then what we want to do now is to build a link between the generalized Euler characteristic, I mean possible cuboid decomposition, I mean a volume point of view in blue here, and the Euler characteristic of the boundary. Okay, so in gray it is a boundary, and in blue it is a volume. Okay, so here it deals with the generalized Euler characteristic, and here it is the Euler characteristic. And here it is the genius of the volume. So there is a link between the generalized Euler characteristic of a volume and the Euler characteristic of a surface. In the topology point of view, what we want at the end, what is the unknown? The unknown is the generalized Euler characteristic of the volume, is the genius of the volume. This is what we want. This is what we seek. This is what we are looking for, okay? So assuming that you have the Euler characteristic of the boundary, then you have a link between the generalized Euler characteristic and the Euler characteristic. Furthermore, you have a link between the number of nodes, the number of edges, and the number of faces of the mesh, the quad decomposition. However, it is not sufficient to build the cuboid decomposition. There is existence, but you have not unicity. Okay, it is not a problem. The only thing to do now is to have one solution of the cuboid decomposition. Okay, so algorithms are available today to do that from a cuboid, from a band decomposition. From a band decomposition and a parameterization of the surface based on Crossfield and quad decomposition, we are ready for building this. For instance, it is in a topological point of view the same thing. What you see on the right is a B-spline solid. A B-spline solid means that it is a B-spline model, not only of the surface, but also in the bulk. So here, you have no more than 4 cuboids, and each cuboid, you recognize here a point, according to this reference configuration. You have 3 holes, 1, 2, and 3, and the 4 cuboids here, and each cuboid on the boundary has a compatible parameterization of the surface and also a parameterization of the bulk. Okay, a parameterization of the bulk, and in the bulk, you have only cuboids. Only cuboids. So quads on the surface and cuboids in the bulk, and all is automatic. And the idea is to have a mapping between this reference configuration and the true mesh based on quad and cuboids. So you can see here the idea is now the ability of such a strategy to make a strong link between different meshes by this reference configuration based on quad, crossfield, and cuboid decomposition in order to build virtual twins on the geometrical parameters. Okay, so we can do that. I mean, B-spline solid modeling of 3D geometries based on quad decomposition of the boundary and cuboid decomposition of the volume. Strong ideas: band decomposition, crossfields, and generalized Euler characteristic in order to build the B-spline solid, I mean the parameterization in the bulk and the cuboid decomposition in the bulk. And all is linked to a reference 3D configuration by a mapping. Okay. And here, more complex examples, all is automatic. You have a BREP here representation of the CAD. I mean, only a spline modeling of the boundary. It is well known for computer design. And then you have an automatic process in order to obtain not only a quad mesh of the boundary, but also cuboid mesh of the bulk. So you have a parameterization of the surface. It is a non-Euclidean parameterization. It is a non-Euclidean manifold. Okay. It is you can have a locally orthogonal an orthogonal basis on the parameterization and also in the bulk, but globally it is not Euclidean, okay, as you can see. However, here, due to the fact that you have a parameterization on the surface and in the bulk, then you have a tensor decomposition on the geometric parameters locally. Okay. We can make a general mapping between a reference cuboid configuration and the true mesh, I mean based on quads and cuboids. Here, now, we are ready for making a link between different meshes. Okay, whatever is the geometry, assuming that we have the same topology, then we have where the idea is to build a reference geometry, which allows the mapping between the reference geometry and all the other geometries. Okay, and by mapping process, in fact, we have done a mapping between geometry A and geometry B in a topology point of view. Okay, some examples apply application to virtual twins on geometrical parameters. Here it comes from large strain. It can be of interest in order to control the shape of a large strain of a mesh, because you can have difficulty to mesh in large strain. And here we have shown that it is a specific application that Pan's decomposition and cuboid decomposition is very well suited for large strain. If it is possible to have such a mesh, it is of great interest for large strain in order to recover to improve the robustness of the simulations. Okay. More interesting, sorry to be fast on this, more interesting is reduced order modeling is virtual twins. In order to have in real time a virtual twin with possible geometric parameters. Okay, I don't know why, but here there is a movie, but I don't know why it doesn't work. Ah, yes, okay. So here is a possible application of this virtual twin of a cardiac cycle of a ventricle, as you can see here. So at different positions of the cardiac cycle, we have 3D imaging and we have different meshes. But here is what we want to have is the same mesh, I mean, in a topology point of view, of each position of at a given cardiac cycle in order to proceed to simulation in real time of such a problem. Okay, as you can see here, a K point is a quad decomposition of the surface. And here, what is nice is that we can proceed. We cannot proceed on a singular value decomposition on the first mesh, but we can proceed to a singular value decomposition on the second one. Or, generally speaking, on a high order proper generalized decomposition on the second one, or, generally speaking, on a sum of a product of 1D functions, a tensor decomposition based on the parameterization of the surface. It is possible to do that because we can make a link between the different positions because we have topologically the same mesh. The same number of nodes, the same number of quads, and so on. So we can proceed to a decomposition on these parameters. And in fact, all the meshes are no more than a sum of product of parameters of values multiply a given mesh. And here, the mesh that you can see are the result of the singular value decomposition, for instance. So these are not the true meshes from the starting step here. These are meshes which corresponds to the modes of the singular value decomposition. Okay, so what it means is that the pink mode here, the first one, is the closest mesh between the different meshes. It is the fundamental mesh, I mean in terms of energy. I mean in terms of the value of the singular value decomposition, singular value, okay? And the other meshes are corrections of this fundamental mesh in order to make a link between the different meshes, okay? So the geometric parameter, virtual twin based on geometric parameters are more difficult to understand physically, okay? So here is the first example of an hybrid twin on such application. So it can be of interest to put on such a geometry physics, okay? Pressure field, the displacement field, or what you want. Here it is only the boundary, but it can be of interest, even for this simple case, to have a virtual twin, okay? Now I want to focus on the 3D case, okay? I use the same tools as explained in the first part. I mean, if you remember, a reduced order model based on high order proper decomposition, and in order to optimize this number of snapshots, I propose to use a sparse grid technique with adaptive multi-grid techniques in order to minimize the number of snapshots in the multiparametric space, okay? We have to optimize the number of snapshots. Here, what is a snapshot? A snapshot is a given geometry. A given geometry, okay? In the possible parameters that we have defined on the geometry. So here, the snapshot is a given geometry. And if we modify the geometry, we have a new snapshot. This is the idea for geometric parameters. And we define the values, the possible values for each parameter, and it defines the hypercube of the multiparametric space for geometric parameters. So at the end, we use the same tools, and we can build the following virtual twin. Here is a very simple engineering application. Okay, you recognize the wheel here that we have already studied before, and here in real time we can adapt the radius, the thickness of different parts, and so on. Here we have more than 10 parameters with we can add mechanical parameters if we want. But what is important to notice here is that now you can see clearly that we have a quad decomposition of the boundary, a cuboid decomposition of the bulk. Furthermore, whatever is the value of the parameters, we have topologically the same mesh on the boundary and the bulk. We have a boundary parameterization and also bulk parameterization, and it is a key point for reduced order modeling and for virtual twins and geometrical parameters. Okay, the same thing. Sorry. Okay, I have to. Come back, sorry. Okay, already done. Okay. Okay. I have to wait for a few seconds. Okay, it works. So here is the same thing. Okay, now we have geometric parameters. And in the virtual twin, we add material parameters. We add material parameters, for instance, the Young modulus. We can add a random load. Okay, the position of the load can be random in a specific domain of values. Okay, why not? And then in real time, we have the solution in terms of 3D fields, for instance, the displacement magnitude on the new geometry. And it is also based on band decomposition, quad decomposition, and parameterization of the surface, and the same thing in the bulk. Cuboid decomposition with bulk parameterization. So the idea of the tensor product, it is a fundamental property that we have used, and it comes from naturally the isogeometric analysis. Okay, so optimization of the number of snapshots, this is not so easy. So I propose here to use sparse grids. In order to reach a given level of accuracy, we can use a specific error indicator. based on the separated variable representation of the virtual twin. Okay, and we can have other kind of examples. Okay, I don't know. Yes, and errors in a geometrical point of view are more difficult to plot. When we compare a field with a reference one, it is easy to understand what is a stress field, but the error on geometric parameters is not so easy. For instance, here we can have localized errors in the mesh, which are not so easy to detect in order to build a mapping between the different meshes, I mean, in the reference one. Okay, so this can involve errors in the virtual twin. So still improvement, place for improvement in the mapping between the reference one and the cuboid decomposition of the true mesh. Okay, whatever is the case you consider, here is a summary of the general strategy. You have initially either a triangulation of the boundary, that's it, or incompatible meshes, why not? There is no compatibility between the interfaces on this mesh. I mean interfaces between different parts of the mesh, okay, why not? Whatever is the initial information on the boundary, we don't care about that. What we want is a cuboid decomposition. First of all, we want a cuboid decomposition. Then with Crossfields, we are able to build the parameterization of the surface, then a quad decomposition of the surface, and then a cuboid decomposition of the 3D volume. All is compatible. We have a parameterization of the surface and the volume, and this is very, very, very well suited for, high order proper generalized decomposition. I mean, an estimate of different meshes based on this decomposition as a sum of the product of 1D functions, a tensor product decomposition of the volume. Okay, so it is a starting point. It is the first attempt of something which is like a dream. It is a strong link between computer and design, in fact. Isogeometric analysis, a mechanical model, a solver, physically based on balance equations, okay? And Redis order model. Redis order model, so this global tool, I think it doesn't still exist. However, it is maybe an interesting point of view in order to develop automatically the offline stage and in order to build automatically a virtual twin, in fact. Okay, in order to build it in a frugal way and then the ability to use it in real time on the online stage. So here, I think that there are many possibilities. It is not yet standard to develop. I mean, a strong link between the geometry, the mesh, and the equations of physics in order to, and also to be not intrusive at a given level of accuracy, to build automatically virtual twins. So it is the first attempt to do that on geometrical parameter in collaboration with ANSYS software. Okay. Maybe I have a last part in my presentation this morning on optimization. So maybe we can take a few minutes now for discussion before concluding this presentation on the third part. So I can take a few minutes if you have a question on this, as you want. If there are some questions on virtual twins with geometrical parameters. So for instance, here, for this problem with the 5 parameters, 200 snapshots were required. On the offline stage, the CPU estimate was close to 30 minutes. And the post-processing step, I mean the online stage, in order to recover the result in real time, the new geometry with a new geometric parameter with a good field. I mean, in terms of linear elasticity, because it is a static problem. It takes 3 seconds to plot the new geometry with the new field. So it is not exactly real time. However, it is quite fast, and it can be enough for preview initial simple using of such a virtual twin. There are still place for improvement for obtaining the solution in real time and so on. However, the global strategy seems to work well in this case. Okay. Another example. Okay, it is another kind of geometry. What is nice in this geometry is that you have globally in terms of topology, 1, 2, 3, 4, 6 holes in this volume. Okay, and in the same way, it is possible, as you can see here, to build a quad mesh of the boundary, and also a band decomposition and so on, Crossfields, and then a parameterization of the volume. And here, according to the 4 geometric parameters in this example, the offline stage concerns is optimized and concerns close to 150 snapshots and less than 1 hour. And here we can obtain the solution, the linear elastic solution of such a problem. Here you can see the displacement magnitude and the deformed mesh in 3 seconds. So it is not also completely real time, but it is very close to real time. And also here in this virtual twin, I think that there is a material parameter. I see the U modulus. So you can modify also the U modulus in this virtual twin. Okay, some conclusion on the possible prospects and new improvements of such approaches. Okay. But I don't think it is required to detail this. Generally speaking, what is interesting here is the strong link that we propose between computer-aided design, meshing, and reduced order modeling for developing a general strategy in order to obtain virtual twins. Okay, if there is no question, I propose to conclude this presentation on virtual twins for mechanical applications. Okay, by a last example, a multiscale example, and the ability of reduced order model also to be efficient for multiscale problems.
So I think there is a question. So yes, here.
Okay.
So this person don't get the point. You try to optimize. Yes.
So
what is the link
yes.
to geometrical optimization methods?
So here, in this case, there is no optimization at that time. I will discuss an optimization of the geometry on the next talk. But here, what we want to have is only a virtual twin with geometric parameter. In other words, you imagine that the radius, the thickness, or a specific length is a parameter of the virtual twin. You modify it, and in real time, you have the new mesh, the new geometry, and the fields put on this geometry according to governing equations. Good physics. This is what we wanted to do here.
Julien, is it all right? I think.
Yes, thanks. My question was, can you hear me?
Yes, you can. We hear you.
Yes.
Super.
So,
Thank you.
my question was, so one of the aim would be, for example, to find the optimal shape with these multiple parameters.
So, in fact, here it depends on what you mean by optimizing. What you want to optimize. For instance, you can optimize the ratio between thickness, between the U modulus and the density. Okay? You want to optimize, you have to define a quantity to optimize. Okay? So when you have such a virtual twin, you can imagine to have an optimization process on the geometrical parameters according to a quantity of interest. Why not? Yes, I agree with you. But it is another step, okay? It is a loop on such virtual twins in order to optimize a quantity of interest. I agree with you. It is another topic, and you can use it, I agree. I mean, this kind of virtual twin for optimization, but it depends on what you want to optimize. I agree.
Any other question? So maybe I can ask a question.
Yeah.
Well, I guess, so you have a refinement adaptive mesh somewhere. How do you manage to, well, when you're going to change the geometry, the gradients are going to change somehow. How do you manage to know that the refinement here will be the good one for the several geometries you will have?
It is a very, very good question, because here it is not yet done.
Okay.
However, I completely agree with you. In order to improve such a strategy, we have to combine this strategy with an error indicator on the mechanical fields. In other words, whatever is the values of the geometric parameters, we have to reach a level of accuracy for the physical fields. I mean the stress field, the strain field, or the quantity of interest. So it has a strong link with the local mesh size. So here we have not used an error indicator on the mechanical fields. However, it has to be accounted for in such a virtual twin. I agree. Yeah.
Okay.
It is not yet done.
So, okay, no other question in the room? Okay, so we can switch to the last part of your talk.
Okay, super. Thank you, Valérie. So here, in fact, what is interesting is this approach is that we introduce, I mean, in the same way as before, a memory effect in computational mechanics on geometrical parameters. Here, now, we are able to build a link between different kinds of meshes. The link between these meshes is only topology, in fact. Okay, and roughly speaking, a link on boundary conditions, on materials, on possible external loads. But it is a starting point in order to make a link between different geometries instead of starting a new calculation with a new geometry. If we keep in mind such an information, we can have a good estimate in real time. And I agree with Valérie, according to the fact that we reach an enough level of accuracy on the mechanical fields. So now, okay, other examples. I propose to conclude this course on virtual twins, physically based or applied to mechanical engineering on different on multiscale computational mechanics. The idea of a virtual twin is very interesting for real-time application, for simulation in real time of processes, for instance, welding, or as we have seen before, geometrical parameters. However, it can also be of great interest in order to introduce something like a memory effect, I mean virtual charts or virtual twins of a specific material. Okay, as you know very well, in computational mechanics, solid mechanics, or the kind of physics, we have different scales. Okay, the scale of the component, the scale of the structure, and also the scale of the material, for instance, in the simplest way. The material, in fact, in the simplest models, is no more than an homogenization of very complex materials at a finest scale. If, for instance, you consider a steel, you have grains and so on. So at the finest scale, you have a high level of complexity. Nevertheless, at the end, you have no more than a U modulus and a Poisson ratio in the linear elastic regime. So the question is it possible to introduce a memory effect to develop specific virtual twins for multiscale problems, there are many ways to use this point of view, either in a bottom-up approach. I mean, you know the finest scale, okay? And you want to build a virtual chart of the material at the finest scale in order to build, for instance, a FE square strategy. I mean, finite element model at the mean field scale based on the ghost points on a microstructure. Okay, and the microstructure can be very complex. So at each ghost point, you make a zoom in the material, and you have to build another finite element mesh of the microstructure and to proceed to complex boundary conditions. And this boundary condition can come from the core scale. Okay, so you have a coarse calculation, and then you zoom. You have a very complex fine mesh of the microstructure based on coarse boundary conditions. So you proceed at the fine scale to a finite element calculation, and for each ghost point, and then you come back to the mean field, okay, the effective scale, and so on. So it is already available in finite elements or in computational mechanics. It is very often used in solid mechanics, or particularly in fluid mechanics with multi-scale effects. But here, what we want to propose is, instead of proceed to bottom-up strategy with complex calculation and strong link between the core scale and the fine scale, or imagine another point of view, top-down point of view. It means that you fix the mean field, and the question is, what is the microstructure that allows to have the given behavior at the coarser scale? Okay, imagine that you prescribe the coarser scale. You want the following effective behavior, and the question is, what is the material that allows to obtain the prescribed stress strain law at the coarser scale? Okay, so either you know the final scale and you want to have the effective behavior, or you fix the effective behavior, and one can wonder what is the microstructure which corresponds to this effective material. Okay. So I will focus on the second point of view. Imagine in the simplest scale, linear elasticity in solid mechanics. You prescribe a mean field, an effective material, a linear elastic material. It can be isotropic, I mean. It can be orthotropic material or anisotropic material. And the question is, what is the microstructure which corresponds to the prescribed macroscopic coarse material? Okay. And also, we can introduce this question in a multiscale optimization. Okay, so it's time for optimization. I mean, not only at the coarse scale, we can optimize the core scale according to density and Young modulus. Okay, so in order to have the minimization on the material, what is the minimum material that is required in order to reach a given quantity of interest, a prescribed displacement or prescribed load. And also, we can imagine in the same loop, not only an optimization of the core scale, the global shape, but also an optimization of the fine scale. In order to reach, at the end, an optimized material, not only in terms of Young modulus, but also in terms of density, at the global scale and also at the fine scale. And here we propose to use a virtual twin at the fine scale. Okay, instead of each time we have an optimization process at the core scale and an optimization process at the fine scale, and then you loop on this multi-scale strategy, we propose to use a virtual twin at the final scale. We store the information, all the possible materials. Okay, and then we use it at the end in a global optimization process where we optimize the core scale and the fine scale. So on the left, you have the bottom-up approach, which is quite standard here. I mean, we assume that we know the fine scale, and what we want is the effective material. So we have a loop between the core scale and the fine scale, but here the fine scale is fixed. Okay, and on the contrary, on the right, it is a top-bottom approach where we want to fix the core scale, I mean in terms of material, okay? We optimize the core scale in terms of density, and also we optimize the material according to a prescribed behavior at the core scale. So the idea is to build a virtual twin or virtual chart in specific parameters, which are material parameters. I mean Young modulus, Poisson ratio, or LaMCoS parameters, or different parameters which comes from the theory of linear elasticity. Okay, and in this virtual twin, each snapshot is a material, and this material is optimized in order to reach given prescribed behavior at the core scale. And we want to optimize the density in order to have an optimization of the material, and then coupled with an optimization of the structure. So here you can see different snapshots of optimization of the fine scale. It can be obtained by additive manufacturing and so on. So such geometries, as you can see, can be complex. Here we assume that the material is at the fine scale is a monophasic material. Okay, so this was done in collaboration with Lyon, Milan, Blan, and the PhD student was Tristan Juraszkiewicz on this topic. So it concerns application virtual twin on innovative micro-architectural materials and application to multiscale topological optimization. I mean, what we want to optimize is the fine scale and the core scale at the same time. In fact, it is important to come back to the fundamentals. I think that you know very well the HB map of known materials. For instance, if we compare the Young modulus and the density, the mass density, clearly the known materials define an area where the two parameters are available, but it seems that there are some materials that are not yet available, where the Young modulus is quite high with, with an optimized density, I mean a small value for the density. So, for instance, here, such materials are very interesting and are studied in detail for more than 20 years and can be obtained at that time with additive manufacturing. Okay, additive manufacturing offers a new paradigm in order to build such materials. I mean architectural materials, because here we have, I think now, the opportunity to print in 3D, even with the steel, with different techniques which are available today, the microstructure of the component at a given scale, which depends strongly on the possibilities offered by the process. So here is an example of micro-architectural material with periodic boundary conditions. And here, such materials are very interesting by their effective behavior. Okay, imagine that you have a very fine scale with such a material. You can obtain at the end, at the effective scale, very surprising materials, maybe which are on this area of the HB map. Here are examples. I give you this example because it is quite standard at that time. It concerns optimization at the core scale. Okay, many methods are available today to do that with different boundary conditions and different loads. Okay, however, it is still interesting to see what happens. The dependency on the boundary condition and the load at the core scale. Okay, so here we assume that we have, for instance, a linear elastic material still. So nothing new on the fine scale, but at the core scale, we can obtain very nice shapes according to the possibilities that we have depending on the boundary conditions and the loads, okay? And all works in 3D here, and it is mainly based on level set approach. Here we use level sets in order to optimize the geometry. And then at the end, it is a compromise between the Young modulus, okay, and the density. So here it is well known for a long time now. Those methods are available at the core scale, and here are examples of such optimization at the core scale with the level sets. But now what we want to do is the same thing plus the optimization of the fine scale, I mean the material. Here we assume that the material is based on 2 parameters. It is still isotopic linear elastic material based on Young modulus and Poisson ratio. But the question is it possible to do better than an isotropic material? I mean, for instance, one can wonder if one can obtain better results in terms of density if we optimize at the same time the microstructure. I mean, we decrease the density of the material. I mean, holes in the materials at the fine scale. Okay, here's an example of a very simple case, but it all is in 3D, it's important. I hope that, yeah, it works. Okay, so here the idea is the following. We give a given, here we propose to follow a given prescribed core scale, I mean in terms of linear elasticity. Here are the components of the hook tensor in the void notation. Okay, so it is very well known. Assume that you give some parameters on the hook tensor. Okay, and then at the end we want to optimize the density. So we have an iterative process. It is exactly the same as before. It is an optimization process, but not. We don't optimize exactly the same Lagrangian, the same quantity of interest, because here we optimize a prescribed effective linear elastic material and the density. And here, what is nice is that we can obtain very surprising microstructures. And such microstructures now can be obtained by additive manufacturing. This is what we hope to have at the end of this process. Okay, more interesting, it is also possible to have here, as you can see, negative Poisson ratio. As you know very well, standard material in nature have only Poisson ratio between 0 and 0.5. It corresponds to incompressible materials for 0.5, but theoretically it was discovered more than 150 years that Poisson ratio can also be negative, okay, until -1. However, in nature, it was not possible to discover a material with negative Poisson ratio. In other words, when you have a tensile test, you have an increasing of the profile uniform along the bar, okay? So in natural material don't offer such a possibility to have a negative Poisson ratio, because in practice, very often what we have is only a positive Poisson ratio. When you have a tensile test, you have a decreasing of the uniform decreasing of the profile. However, with such materials, imagine that you prescribe the core scale with a negative Poisson ratio, the algorithm finds a solution. The algorithm finds a solution, and this is what we call an auxetic material. An auxetic material is a material with negative Poisson ratio, and here it depends if the material is not isotropic. Here we have an isotropic material, so we can have different Poisson ratio, okay? And some can be positive and some can be negative. Okay, so depending on the case A, B, and C, in case A, you have all the Poisson ratio are negative. Okay, it is an anisotropic material in the hook tensor. B, you have three specific Poisson ratio negative and the same for C, but not the same values. Okay, all the values are between -1 and 0.5, and the algorithm build a new material which is auxetic, and it depends on the, I don't know the word auxeticity. I don't know exactly if it is not a good word. However, there are different kinds of auxetic materials, and then you obtain different kinds of microstructures. And in order to show you the auxetic ability of the material here, I mean to have a negative Poisson ratio. Here you can see on the right a movie. I hope it works. Oh. Uh-huh. Okay. I think that it is the end of the morning, so the computer seems to be quite.
Il faut que tu cliques avec l'arrière du crayon.
Ah, ok.
Vraiment sur le crayon sur la gauche là-bas. Ça peut marcher.
Because it was working. Okay. Okay. Unfortunately, it doesn't work. I will try to find another example. Sorry. So I hope that. Yeah, it works. I have a problem with the movie. Okay, sorry. So what we can see in such a movie is that when you proceed to a tensile test on this micro-architectured material, you have an increasing of the profile, okay? And this can be obtained by such micro-architecture. Okay. In a mathematical point of view, it is possible to write in terms of Lagrangian minimization of functional, the optimization at the coarse scale, and the optimization at the fine scale. It is not exactly the same problem. On the left is a standard optimization of the coarse scale. I mean in terms of Young modulus and density. So you can see in the Lagrangian that you have something close to the elastic energy, and here an optimization on the volume of the material, and you can define a parameter if you want to have a specific compromise between elasticity and density with the reference problem on the coarse scale. And here is the problem on the fine scale. In order to optimize with a specific condition, you recognize here periodic boundary conditions, the material at the fine scale with a similar shape Lagrangian, the shape of the Lagrangian. However, it is an optimization of the fine scale. And the idea is to have an iterative process between the two scales. Some examples. Here, if you remember the bending test, it is a standard bending test. You assume that the starting point is a rectangular geometry with a clamped part on the left, I mean prescribed displacement to 0 on the left, and on the right you have a bending load in the middle of the right of the geometry. And here is a standard optimization of the coarse scale. It is quite well known that we obtain such geometries. And in the same way, we have a complex algorithm because we have to optimize both the geometry at the coarse scale and also the geometry at the fine scale, because we don't know in advance the material that is optimized for such a problem. So it can be very slow, in fact, because if you proceed to an estimate of the optimization of the coarse scale and at the same time the fine scale, and it is nonlinear, in fact, if you proceed to coarse estimation of the CPE that is required in 2D and in 3D, it can be very slow. So the idea is to put the optimization, instead of optimizing at each iteration the fine scale, we put it in a virtual tree. We want to put the optimization of the fine scale in a virtual tree. And then at the end, what we hope is to only proceed to an optimization on the coarse scale and to have in real time, in a virtual chart, the information of the good fine scale already optimized, a memory effect, that we put on the fine scale, instead of calculating each time the good microstructure, we put it in a virtual twin. So at the end, what we want to have is a very, very fast algorithm only on the core scale, where the fine scale is already optimized and put in the virtual twin. And then now, with such an idea, we hope that it is possible to proceed to double optimization of the course on the fine scale. But here, the price to pay is to build an offline stage, a learning stage of microstructures, and put this information in a virtual twin. Okay. Here are examples of such a strategy. We use the same strategy as before. We build virtual twins of the fine scale. According parameters which come from linear elasticity, we optimize the density at the fine scale, and we build a vademecum of different kinds of microarchitectural material, according to negative Poisson ratio, positive one, anisotropic one, and so on, according to the theory of Hooke tensor. It is not a simple tensor, the Hooke tensor, because it is a four-dimensional tensor. So a good idea can be to build such virtual twins on the decomposition, the tensor decomposition of tensors of order 4. And it is quite complex because there is no unicity. When you have the decomposition of a tensor of order 4, there are many theories for that. However, the idea is to have the smallest virtual shaft, virtual twin, which contains all the possible materials of the Hooke tensors. Anyway, imagine that it is possible to do that. We proceed to an offline stage in order to learn the different microarchitecture and materials in 3D. And then, on the optimization process of the core scale, we hope to obtain the information of the optimized material at the fine scale in real time. Here we compare different meshes used on the core scale for the level set optimization of the core scale. We have observed that you have a low dependency. Sometimes you can have a dependency on the initial mesh, but it converges when the mesh becomes fine. It depends on the result at the that you obtain after the optimization of the core scale. Okay, but now what is new is that at the same time, in real time, you have optimized the fine scale, I mean the material. So it consists in data assisted offline online design optimization. Here, what is nice also to understand is during the nonlinear iterative process of the optimization of the effective scale, the core scale, the microstructure, the good microstructure is not always the same. Okay, during the iterative process, sometimes we have this kind of microstructure, and sometimes you have this one.
You have an interesting question.
Okay, super. I have a question about the coupling between macro and microscale optimization. For example, is there a different solution if we begin by one or another scale in the first optimization step? I'm not sure to understand well the question. I mean, by one or another scale, I mean the coarse or the fine. Because here it is clear. Okay, thank you, Julie. So, in fact, it is clear that here we put the memory effect in the material. I mean the microarchitecture. I'm not sure that it is of interest to build a virtual twin on the core scale. Because the core scale depends on boundary conditions and so on. It can be very complex, many possibilities for geometry. So I don't know how to build a virtual twin on the core scale. I don't think it is so simple. This is the first comment. So the idea is only to build a memory effect in the finer scale in order to store this information and to use it after building a virtual twin, I mean an offline stage. However, if I understand the question, Here, the algorithm is based on an iterative process on the coarse scale and the fine scale. So we optimize in the same time the two scales. I mean the coarse scale and the fine one. This is the reference problem. We assume that we are able to solve this very complex problem, and it converges when the size of the fine elements tends to 0. And at the end, what you have is something which is optimized on the coarse scale and the fine scale. And on each ghost point, you have a microarchitectural material which is also optimized with a mesh which converges when the size of the elements tends to 0. So it is a fully nonlinear problem. And we have proved that, we have studied this, in fact. The question is, if I put the finer scale on a virtual twin, does it turn to the same problem? Maybe it is a question. The answer is yes, if we assume that the virtual twin of the fine scale is accurate enough. Is accurate enough in terms of mesh and modeling of the microarchitectural material. And in this case, if we store the good information instead of this optimization process, then the nonlinear loop is the same, turns to the same solution if you replace this calculation by a virtual twin. Yes, I hope that it is clear. So the mesh dependency of the coarse scale and also the fine scale. We have there is already, however, there is a global difficulty in optimization. Don't forget that even on the coarse scale or the fine scale, there is not unicity. There is no unicity, so clearly, sometimes you obtain a given solution or another one because the solution is not unique. So even for the material, the solution is not unique. However, when we have a solution, we assume that it is a good estimate. But we have also to keep in mind that the solution is not unique on the coarse and the fine scale. Yes. And furthermore, the combination of the two. So I have to conclude. I think it's time to conclude. Yes. Here, this morning, here this conclusion is quite general. Data-assisted computational mechanics approaches are efficient tools to deal with the following challenges. In fact, first of all, the high-dimensional multiparametric spaces that we have used in the virtual twin for the simulation of process, for instance, welding, and also geometrical parameters, and at the end, optimization of multiscale optimization of microarchitectural materials. It is clear that 10 for the dimension of the multiparametric space is already challenging. I don't think that with such approaches you are able at that time to reach a dimension close to 10 to 100. Okay, there is still place for improvement, I think, in order to reach high dimensional space. I mean, close to 100. This is quite challenging. Furthermore, here we main constraints that I want to keep in mind on such hybrid virtual twin, is that we want to build virtual twin physically based. I mean, with a strong physical content. I mean, balance equations, fundamental equation. Even in the data-driven case, I assume that unfortunately in solid mechanics, all the data that are required to build a virtual twin are not available experimentally. This is why we have to combine fundamental laws in physics and possible data, but we are not in the case of big data for such applications. So be careful to big data in this case. In fact, in practice, even with field measurements in 2D and 3D, I think that data are not enough. There is not enough information, particularly for stress, in order to avoid balance equations. Okay, thank you for your attention.